Hi there, welcome to Raylene Maths. In this video we will look at solving polynomial equations. To get started, let's take a look at the parabola at right. We notice that it doesn't have any x-intercepts, which means that it doesn't have any real roots. And so no x-intercepts, which means no real roots, means that the quadratic discriminant b squared minus 4ac is going to be negative. And we want to write the equation of the function, and then we can confirm that discriminant. So here we have that the basic parabola y equals x squared has just been shifted up one space. So the equation of this quadratic function, or quadratic polynomial, is y equals x squared plus 1. And so from here, we could just work out the quadratic discriminant to confirm, and we see that the discriminant is b squared minus 4ac, which is going to be 0 squared minus 4 times 1 times 1, which is negative 4. So indeed, the quadratic discriminant is negative. So if we want to solve for x when y is equal to 0, we substitute y with 0, and since x shows up only once in this equation, we can use square roots to isolate for x. So we get x squared is equal to negative 1, and if we take the square root of both sides of the equation, we end up taking the square root of a negative number. This actually gives us the absolute value of x on the left-hand side, but then we have this unfamiliar structure, this square root of negative 1. Up until now, we've said that a number like this doesn't exist, and that's true within the real number system. But let's take a look at a new number system. Real numbers are the set of rational numbers and irrational numbers. Rational numbers are ratios of integers, like 2 over 5, or 3 over 1, or negative 7 over 2. And irrational numbers are numbers that are not rational or fractions of integers. And those numbers, like pi and the square root of 2, never terminate or repeat with a pattern as a decimal expansion. We might think of the number pi as a geometric idea, which says you take the ratio of the circle, any circle, divided by its circumference, and that ratio is called pi. Or we might talk about the square root of 2 as a geometric idea. If we have a square with an area of 2, the base or the root of that square, the foundation of that square, is the length, because we need 4 lengths that are the same to form a square. And the root or foundation of that square with area 2 is a length of square root 2. So we can come up with the circumference divided by the diameter, or pi, or the square root of 2 as decimals, but they are decimals that will never ever end, terminate, or repeat. So altogether, those are the numbers that we've been working with up until now, the real number system. But we can come up with another idea of a number, and that idea of a number is a number that we can square to get a negative. And so it's been decided that a number I should be invented that when we square it, we get negative 1. This means that the square root of negative 1 is equal to I, and this I is our base imaginary number. So now let's use the quadratic formula to solve x squared plus 1 equal to 0 using imaginary numbers. We have that a is equal to 1, b is equal to 0, and c is equal to 1. So from the quadratic formula, x equals negative b plus or minus the square root of the discriminant, all divided by 2a. So here we get negative times 0 plus or minus the square root of b squared, which is 0, minus 4 times 1, all divided by 2 times 1. And so we have negative 0 plus or minus the square root of negative 4, all divided by 2. And from here we can rewrite the square root of negative 4 as the square root of 4 times negative 1, and then we can break this apart into 2 square roots that are joined by multiplication. We can rewrite the square root of 4 as 2, and the square root of negative 1 as this imaginary number I. And from here we get plus or minus 2I divided by 2, and therefore x is either equal to, so we get plus or minus I, which means that x is either equal to negative I or positive I. Now there's no place to graph or plot these numbers, because when we draw a graph, we have a real number line for x and a real number line for y. So there is no place for non-real numbers like plus or minus I. So let's take a look at another example where we have a different quadratic with a b value that's not 0. And if we work out the discriminant here, we get b squared minus 4ac gives us 2 squared minus 4 times 1 times 5. And we end up getting 4 minus 20, which is negative 16. And because the quadratic discriminant is negative, we will have non-real roots, which means we could have, or we will have, imaginary or complex roots. So if we use the quadratic formula, x equal to negative b gives us x equals negative 2 plus or minus the square root of the discriminant, which is negative 16, all divided by 2 times a, which is 2 times 1, which is 2. And similarly, we can rewrite the negative 16 as 16 times negative 1, and then we can pull apart those two square roots so that we get x is equal to negative 2 plus or minus the square root of 16 times the square root of negative 1. I'll just break that apart into two square roots. And the square root of 16 is 4, and the square root of negative 1 is called I. So from here, we take the 2 and we divide it into both terms in the numerator. So 2 divides into negative 2 as well as into 4i. And that gives us that x is equal to negative 1 plus or minus 2i. Now, technically, numbers that are combinations of real numbers plus imaginary numbers, like we have here, we have a real number part and we have an imaginary number part, and we are adding or subtracting those parts. This is not a purely real nor a purely imaginary number, and so the name that we give to such numbers are called complex. But often textbooks will just say that any number involving I is called an imaginary number. So be wary of the term. Technically, this number is not imaginary and it's not real, but it's a combination, so we call it complex. Okay, in this question we're going to solve for the roots of the polynomial equation x to the 5 plus 4x cubed equals 5x to the 4 minus 2x cubed. Now we're going to do this by getting all the terms on one side and setting equal to 0. So we have x to the 5 minus 5x to the 4 by putting the terms in decreasing order of exponent, plus 4x cubed minus a negative, so plus 2x cubed. That's all equal to 0. And when we look at this polynomial on the left-hand side, we see that we have a common, two like terms, so we're going to simplify those. And then we are going to find a common factor of x cubed. So when we factor the x cubed out, we will have a quadratic left-hand side, x squared minus 5x plus 6. And we can factor that as x cubed times x minus 2 times x minus 3. Now we see that we've got exponents on each of these factors. The first factor, to be really clear, is actually x minus 0. And I'm just going to put the exponents on those factors in red. So the first exponent is 3, the second exponent is 1, and the third exponent is 1. So this tells us not only the roots, but also the multiplicities, or the number of times that those roots occur. And so coming from the first factor, set equal to 0 by the zero product property, we get x equal to 0 occurring with a multiplicity of 3. And then we have, we have x equal to 2 occurring with a multiplicity of 1, because that's the exponent. The number of times that that factor occurs is 1, so the number of times that that root occurs is 1. Or we have the third root, or 0, x equal to 3, occurring with a multiplicity also of 1. Now the multiplicities here just help us to see the shape of the graph. If we have a multiplicity 1 shape, or a root occurring one time, the graph would have a shape at the x-intercept that looks like this or like this, depending on the direction that the graph is coming from. If we have an even multiplicity, such as multiplicity 2, the graph is going to turn around at the x-axis. So we have an x-intercept that looks like a parabola shape when we zoom in at that point. It's not necessarily a parabola, because if we had a multiplicity of 4, for example, the graph would be a bit flatter, but it would still turn around. And in the event that we have a multiplicity 3 or some higher odd exponent, like 5, we would have the graph flattening out and having a horizontal tangent, but then continuing through. Or it could be upside down, depending on the direction that the graph is coming from. And here, for example, if we had a 5, then this would be even flatter. I made that quite flat already, so it's kind of hard to make it even flatter. But the idea is that the graph would be flatter looking along here at the x-intercept. Okay, so that just gives us a bit of information about the multiplicities, and while we're at it, let's just take a look at the graph of this polynomial if instead of having a 0 here, we still had y. So if we substitute y with 0, we're looking for zeros of the function, otherwise we're just graphing the whole function. Let's see how these multiplicities coming from these factors at these roots make the graph look. Okay, here we have the cubic polynomial multiplied by the linear times the linear, and we see that at the x equal to 0 x-intercept, we have this flattening of the graph and then continuing through, which is characteristic of an x cubed or a negative x cubed shape. And then the graph turns around somewhere at a relative maximum point and then continues smoothly through the next intercept without flattening or turning around, and that's because this root has a multiplicity of 1, which is indicated by the exponent here. I'll make it explicit by putting the exponent of 1 there. Then the graph turns around somewhere at a relative or local minimum point. It's not the overall minimum point because it's not the smallest or lowest y-coordinate of the entire graph, because over here we have even lower y-coordinates. But then the graph will go smoothly through the x-intercept or root at x equal to 3, as indicated by the exponent on that factor, x minus 3, which is raised to the 1. The other thing to note here is that we have a leading term which would have the same end behavior as the monomial x to the 5. So if we were to expand this polynomial here, and I think we can do it in this program, if I just click expand, then we can see that the leading term is x to the 5. So if we just focus on that graph of y equals x to the 5, we see that as x goes to the left on the purple graph, y goes down, and as x goes to the right on the purple graph, y goes up. So it's now a black graph because I have the red and the blue graph overlapping, but I'll make it just the red graph for now. That graph has the same end behavior as the leading term. And so whether we have the polynomial in standard form, like the red one, or in factored form, like the blue one, the end behavior of x to the 5 would be the same shape as the y equals x to the 5 single function graph. In order to solve polynomials by factoring, we want to be able to recognize some special cases of factoring, such as these special products. We've got a perfect trinomial coming from squaring a binomial, which means a plus b is multiplied by itself. And when we expand, we get the trinomial of a squared plus 2ab plus b squared. And we're going to see that recognized down here as x squared plus 6x plus 9. So this is really x squared plus 2 times 3 times x plus 3 squared. And so we can see that this is following the same format where a is like x and b is like 3, and so we get x plus 3 quantity all squared. If we can go from a perfect trinomial to factoring a binomial squared, we can solve the polynomial easier. The next case is difference of squares, and here if we were to expand one by one, multiplying all the terms through, we would get a squared minus ab plus ab minus b squared, and in this example the middle terms of negative ab plus ab equals 0. So we're left with what we call a difference of two squares, a squared and b squared. And so we have an example of that down here, 36x squared minus 49. The first thing we should look for is any common factor, but we don't have a common factor between 36 and 49, so we can just start to set it up as the two products, or the two factors. And we're looking for the two factors that have opposite signs in between, but the same first and second term. We refer to those as conjugates. Conjugates have the same two terms inside the brackets, but opposite signs. So then we take the square root of 36x squared, which is 6x, and it goes in the first spot of both brackets, and the square root of 49, which is 7. And so this guarantees that the middle term will cancel, and we will be left just with 36x squared minus 49. The next two special products are called the sum of cubes and the difference of cubes, and both of them have a binomial multiplied by a trinomial. And in fact, the only difference between them are the signs here and here. And so if we're starting off with, if we want a sum of cubes, we have a plus in the first bracket, and a difference of cubes will have a minus in the first bracket. Okay, so when we expand, we take the a and distribute it through the second bracket. We get a cubed minus a squared b plus ab squared. and then we take the b and we multiply it through. I'll do it in a different color. So we get ba squared, or plus a squared b, and then we get negative a times b squared, and then we get positive b cubed. And we notice that all of the terms except for the first term and the last term will sum to 0 or cancel. And so we're left with this sum, this addition of cubes, a cubed plus b cubed. Now we can use that to factor x cubed plus 8, which we can recognize is going to be something cubed plus something cubed. And we have an x in the first bracket and a 2 in the second bracket. So a is like x and b is like 2. So when we factor it, we're going to get x plus 2, so the cube root of the first term, the same sign as the original expression, and the cube root of the second term. And then to get the trinomial, we square the first term, we multiply the x and the 2 together and change the sign, so we get minus 2x, and then we square the last term. So it's different from squaring a perfect trinomial, or squaring a binomial to get a perfect trinomial. So this gives us the factoring for the sum of cubes, x cubed plus 8. Now the case for the difference of cubes is the same, except the signs that are highlighted are different. So here when we expand, we are going to get a cubed plus a squared b plus ab squared. And then distributing the negative b through gives us negative ab squared, rather negative a squared b for that one. And then the negative b times the positive ab gives us negative ab squared, and then negative times positive b cubed. So all of the terms that cancel here are the middle terms, and we're left with a cubed minus b cubed. And so that's the case for the fourth and final factoring down below. X cubed minus 27 we can see is going to be x in brackets cubed minus 3 in brackets cubed. And I'll just put that one up here. So I'll do it in green so it stands out. And we have that x in brackets cubed minus 3 in brackets cubed factors according to a binomial times a trinomial. We take the cube root of the first term, the sign in between stays the same, and the cube root of the second term. And then to generate the 3 terms of the trinomial, we square the first, we multiply the x and the negative 3 together, and we change that sign, because we want a positive here, and then we square negative 3, which gives us positive 9. If we expand that, we'll get back to x cubed minus 27. So now that we have this special factoring, we want to solve these polynomial equations set equal to 0 for the zeros that are complex numbers involving I. And so the first thing I notice is that I can factor x cubed plus 8 as x plus 2 times x squared minus 2x plus 4 equal to 0. And then from that, either x plus 2 equals 0, or x squared minus 2x plus 4 is equal to 0. And from the first equation, I get one root of multiplicity 1, x equals negative 2. And we can check the discriminant for the second quadratic factor, and the discriminant here is going to be negative 2 quantity squared minus 4 times a times c, and the discriminant is 4 minus 16, which is negative 12. And so the discriminant is negative. We cannot factor, and we have to use the quadratic formula to find the complex solutions. This being negative, this discriminant being negative, means we have non-real solutions. And so coming from the second piece, we will have x equals negative b, which is negative negative 2, plus or minus the square root of the discriminant. Now I'm going to make this discriminant negative 12. I'm going to write it as 4 times 3 times negative 1. And then I'm going to divide by 2 times a, and a in this case is 1, so that gives us 2. Now to simplify here, we can see that the square root of a product is going to be the product of the individual square roots, and so I'm just going to cross out the big square root, and because we have multiplication and not for addition, we can make this 3 square roots joined together by multiplication. The square root of 4 is 2, the square root of negative 1 is I, and the square root of 3 remains the square root of 3. So I'm going to write this as 2i square root of 3, and then all of that divided by 2, and that 2 divides into both terms into the numerator. It distributes. And so I'm just going to put the terms in the numerator in boxes, and then I'll divide each of those green boxes in the top by 2. So we end up getting x is equal to 1 plus or minus I root 3. And so there we have the solutions, either x equals negative 2 or x equals 1 plus or minus I root 3. Now, whenever we have non-real roots, this means that we do not have x-intercepts coming from here, but we do have an x-intercept coming from the real root at negative 2, 0. We can check the graph of a polynomial just to see that if 0 were equal to y, that the graph of y equals x cubed plus 8 does indeed have only one x-intercept. Here is the simple graph of y equals x cubed, and if we add 8 to it, we can see that the graph has shifted up 8 spaces, or vertically translated 8 spaces, but this graph has only one x-intercept at x equals negative 2. Another technique that we can use to help us in factoring is called the method of substitution. Anytime that we see an expression repeated throughout an equation more than once, we can let it equal something else. So for example, in the case of x to the 4, we have x squared quantity squared. And so we see we have another x squared, and just because I know I'm solving a polynomial, I'm going to get the 4 to the other side. Now I recognize that the x squared occurs twice, so I'm going to let another variable, maybe a, as long as I use a different letter, represent x squared. So my equation now says a squared minus 3 times a minus 4 is equal to 0. This is a quadratic equation in the variable of a, whereas the original polynomial equation was a quartic equation, degree 4, in the variable of x. So now I can factor my quadratic, and I see that I get a plus 1 times a minus 4, and that makes sure that I get the middle term of negative 3a. And the zero product property says that a is going to equal negative 1, or a is going to equal to 4. Now, when we're solving, make sure that you don't drop off the equals sign. Make sure that you maintain the equation here, so don't drop this off. And also make sure that in between your roots coming from the zero product property that you use the word or and not an and not a comma. Now our goal was to solve for x, so once we have the values for a solved, we have to back substitute and replace a with x squared. So we have x squared equals negative 1, or we have x squared equal to 4. So x shows up in the first equation only once, and we can take the square root of both sides. And when we do that, we are going to get that x is equal to plus or minus I, the imaginary number whose square root is negative 1. Or from the second equation, if we take the square root of both sides, we're going to get that x is equal to plus or minus 2. So altogether we have 4 different solutions, but as a polynomial function or graph, we would only have 2 x-intercepts, and those x-intercepts would be at negative 2, 0, or 2, 0. There would be no x-intercepts coming from the non-real roots. Okay, let's take a look at the other example. We have x squared times x plus 1 all cubed equals 5 times x plus 1 all cubed. Here we see that the x plus 1 all cubed is repeated, and so we can let that be called a in this example. So if we let a equal x plus 1 all cubed, then we get a new equation that's a partial a and x equation, and it says that x squared times a equals 5 times a. Now, we might be tempted to divide both sides by a, but we have to be careful of division. We can never divide by 0, and because a is a variable, x plus 1 is a variable, we don't know if that variable quantity equals 0. So don't ever divide to solve. Instead, we see that we can take everything to one side of the equation where we have a common factor. And so we take out the common factor, and we get that x squared minus 5 gets multiplied by a. Now at this point we can replace a again with x plus 1 all cubed, or we could apply the zero product property that says x squared minus 5 is equal to 0, or a is equal to 0. Once a is isolated, this is when we can back substitute. So solving this next equation, x squared will be equal to 5, and we could solve this by factoring or by directly taking the square root of both sides. I'm going to actually show you 2 different ways. So I could show you applying square roots, or I could show you by factoring. So I'll just put the instructions here. By factoring, we would have difference of squares, so it would be x plus the square root of 5 times x minus the square root of 5 equals 0. And this is because we have conjugates, the middle term will disappear, and even though 5 is not a perfect square, it is a square of the square root of 5, meaning square root of 5 times square root of 5 gives us 5. And so from the red version, we either get that x is equal to negative root 5 or x is equal to positive root 5. Or if we just work from the square root here directly, we take the square root of both sides, and technically this gives us the absolute value of x is equal to the square root of 5, and then this is really absolute value of x minus 0. So x would be equal to 0 plus or minus the square root of 5. Either way, we can get the same solution for the first equation, x squared minus 5 equals 0, and that solution is that x is equal to plus or minus square root of 5. So we've got method 1, taking square roots directly, method 2, factoring difference of squares. Now the third case is really only the second equation, and we have to back substitute a with x plus 1 all cubed. And if we do that, I'm just going to write it over here so that it doesn't get in the way here. We get x plus 1 all cubed is a factor of x plus 1 with a multiplicity of 3, and therefore the 0 or the root is x equals negative 1 with a multiplicity of 3. And so this is a real root, so we would get an x-intercept at negative 1 comma 0, and it would have a shape of a multiplicity 3 graph, which would look like one of these depending on the direction that the graph approaches the x-intercept at. We would also have x-intercepts at root 5 comma 0 or negative root 5 comma 0. Each of those would have a multiplicity of 1. And so we would end up getting 3 x-intercepts. Even though the question didn't ask for x-intercepts here, it was only asking for solutions. We were stating the multiplicities, but we've gone a little bit further to talk about what the shape of those graphs would look like at the x-intercepts. In number 7, we're asked to use graphing technology to determine the real solutions to this equation. So since we're talking about real solutions, or real roots, or real zeros, we're actually referring to the x-intercepts, places where the polynomial graphs would cross the x-axis. Now, there's actually two ways that we can interpret this problem, and so we'll look at method 1 and method 2. Method 1 first says, let's take a look at the left-hand side as a graph and the right-hand side as a different graph. So I'm going to color code the left-hand side as x cubed plus x squared in blue, and then the right-hand side is a linear polynomial, x minus 1 in red. And so I'm going to let this be equal to y in red, and the left-hand side be equal to y in blue. What I'm going to do here then is intersect two graphs, a blue graph and a red graph. And I'm actually doing the opposite of eliminating y. I am reintroducing y because there was no y in the original problem. And so I'm now going to be looking at two graphs, a blue graph and a red graph, and I'm looking for where those two graphs intersect. So we're going to do that with technology. You can go to any graphing technology, Desmos is popular, or your own handheld device. And so here I have another program called Graphing Calculator, and when I plot the blue graph and the red graph, I see that they have only one intersection point. And so the programs typically lock onto that intersection point, and we can see that the intersection point coordinates are roughly negative 1.8, comma negative 2.8. Okay, we wanted to find the solutions to that real equation, and we said that we had negative 1.8, comma negative 2.8 for the intersection points. And we might want more decimal places, but that'll do for now. And then when we're talking about solving this actual equation, again, we noticed that there was no y here. So we were only looking for the values of x that made the blue graph height, the blue y and the red y, be equal. So what is the value for x we're finding? We're looking for the value of negative 1.8. So by the grapher, our solution is x is approximately negative 1.8. So the first method looked for the x-coordinate of the intersection point, or points, of the two graphs. Now we're going to look at another method where we don't really have two different polynomials, but we only have one. And that is by the method of taking all of the terms to one side. So we get x cubed plus x squared minus x, and then plus 1 is all equal to 0. And I'm actually going to color code the right-hand side in red. So we have our polynomial y equals x cubed plus x squared minus x plus 1. And we are actually still intersecting it, but this time we are intersecting with y equal to 0, which is the x-axis. And so we're really looking for the zeros of, or the roots of the x-intercepts, or the x-intercepts of the blue graph. And so we can look at another system of two equations, a red and a blue graph, and look for the intersection points. The specific intersection points now, when we are intersecting with the x-axis, those points are called the x-intercepts. And so we have the x-intercept here at negative 1.8, and the y-coordinate of that point is 0. So if we label the coordinates of that point, negative 1.8 comma 0, it's not a surprise that the y-coordinate is 0 because we are intersecting y equal to 0 or setting y in the polynomial equal to 0. And again, we are only interested in the value for x, which makes this equation true, which is also the value for x that makes this equation true. So in the end, our solution is still x equals, or approximately equals, negative 1.8. So whether we found one polynomial and its zeros, or two different intersecting polynomials and their intersection x-coordinate, the answer is still the same. In number 8, we have a word problem, and we're going to start off by defining some variables. We want to determine three consecutive integers whose product is 480 more than their sum. So for the integers, we often use x and y. I like to avoid using x and y at the beginning of problems, so I'm just going to let the first integer be a. And so from here I'm going to come up with the next consecutive integer, which means that it's one more than that. So a plus 1, and then one more than that would be a plus 2, be the second and third. Okay, so I don't want to write all sorts of words out, so I understand what that means. And I want their product, which is the answer when we multiply, to be 480 more than their sum. And their sum is the answer when we add. So from here, we're going to come up with an equation. We see the word is, and that means equals, and the product is 480 more than their sum. So I might actually just write that out in kind of a shorthand code. Product is 480 more than, that means we start off with the sum and we add 480. So if the product is more, you need to add to the sum to make those two quantities equal. And so I could just write product equals sum plus 480, and then the product is going to be these three integers multiplied together. So a times a plus 1 times a plus 2, and that will equal the sum of those numbers, which is a plus 1 plus a plus 2, and then add the 480. So now we're going to solve this equation for a. So we can expand this by hand, and we'll leave the a outside at the end. Better to leave that and then multiply through, so you get a squared plus 3a plus 2 altogether, which is then going to give us a cubed plus 3a squared plus 2a. And on the right hand side we have 1, 2, 3 a's plus 3 plus 480, which is 483. And then we could subtract 3a and 483 to get everything on one side equal to 0. And so from here we get a cubed plus 3a squared minus a minus 483 equal to 0. Once we have our equation set up, then it's a good time to reintroduce x, but better not to do it at the very beginning. So now that I have only one variable as an input, I'm going to reintroduce x, because then x can be my graphing variable, and we get that x cubed plus 3x squared minus x minus 483 is equal to 0. And that 0 is going to be my y equal to 0, or my x-axis, which means that I'm going to be looking for x-intercepts of this polynomial. So you can go back to any grapher and you can look for the zeros of the polynomial, or you could have left it in the form where you had a term or a polynomial on the left intersecting with a different polynomial on the right. So here's our polynomial, but we don't see a lot of it. So we could try to zoom out, or we could try to change the window dimensions to see a better view of the graph. And in this case, I don't really know what y values I need, so I might just go from negative 100 to 100 for y for now. Doesn't seem to give me much. Maybe I can go even bigger, say negative 1,000 to positive 1,000. Then I start to see a little bit more of the graph. Maybe I can zoom out from here. And so it's suggesting to me that it is a cubic graph shape because it's flattening here somewhere, which means I will have only one x-intercept. And so if I click on that x-intercept, I get 7, 0. So it looks like my x value is equal to 7. And if we go back to the problem, we solve this by technology and we get that x is equal to 7, which means that my other two numbers are going to be x plus 1 equals 8 and x plus 2 equals 9. And so the product of those is going to be 480 more than their sum. We can confirm that numerically with a calculator. So to check our product, 7 times 8 times 9 is equal to 504, and 7 plus 8 plus 9 plus 480 is also equal to 504. So it looks like we found our 3 consecutive integers that solve the problem. So we can see that there's a variation of using analytical or by hand methods and graphing technology methods for working with polynomials. We can model polynomial equations and then use the solving by factoring or by graphing to find their solutions. That's all for now. Thanks for checking out Raylene Maths.